I'll switch off the camera so that the internet connectivity be better. Yeah, thank you. Fine. So I think transfer learning has already been discussed, right? Has already been discussed by other speaker. But there are few things I would like to highlight before the hands-on session of the transfer learning. So we must have also knowledge on transfer learning and why transfer learning and what are the different factors that you should consider while applying this transfer learning strategy. Then I will discuss attention mechanisms, right? So what are the different types of attention mechanisms we have, and there are a few case studies, right, which we have been working since long time. I've only chosen two case studies just to showcase that how attention is helping the convolutional neural network for improving the performance. So here is just a glimpse of work which we solve at our Vision Analytics and Pattern Recognition Lab at MNIT Jaipur. So you can just look at most of the works are mainly focusing on analyzing medical images. There are also a couple of works on hyperspectral imaging, facial expression recognition, optical character recognition, and as well as video processing. Fine. Before I discuss the transfer learning and all, let me first discuss the limitations working with the convolutional neural network. So what are the major limitations we face while working with convolutional neural network? So what we have observed even yesterday that convolutional neural network demands huge amount of parameters. And we have seen there are architectures like AlexNet, VGGNet, Inception, ResNet and all. So they are asking or they're demanding even more than 50 million. Sometimes it is 60 million. VGGNet is asking for 138 million parameters like that. Optimization, ultimately we want to update all the parameters, and the optimization of these parameters is really difficult, which requires careful parameter initializations as well as hyperparameter tunings. We have also seen there are a couple of hyperparameters we have which need to be tuned or which need to be decided by us. So what happens sometimes if you are dealing with a limited data set having limited amount of data, so your model may suffer from overfitting problems. Right? Because the data is less, but the number of parameters is too high. And sometimes it also takes a lot of time or long time, right, for training, for building the model. So that means the computational power is also high. You can also see over here that AlexNet, right, was taking around 5 to 6 days, right, for training process on 2 GTX 583 GB GPU. So you can take VGG was taking like 2 to 3 weeks of time, right? Although it was implemented on 4 NVIDIA Titan Black GPU. So that means there is always a concern that how to optimize such a large number of parameters here in convolutional neural network and how to initialize those parameters, right? So there are few approaches you will find if you go through the literature like Clorot and He initialization as such initialization technique or parameter weight initialization techniques, which has been shown to provide better results compared to the random initializations which do. So we need to explore that what do you mean by this Glorot and He initializations, right? It is even easy to introduce into the code. If you want, you can also design the filter mask or especially the coefficients of the filter by yourself. If you are a domain expert, right, in the field of, let's say, engineering, or probably you know how to decide or what type of coefficient you should consider for your particular problem statement. If you're having domain knowledge, so you can just come up with your own filter, but you know that yes, it is again manual. It may be difficult, right, to decide all the time what should be the coefficient of each of the filters. But based on some domain knowledge, if you have, then you can decide also the kind of edge-based filters, whatever you have seen yesterday or day before yesterday, or probably the shape-based of feature, or you can say the filters. Those are helping us in improving or extracting the safe information from this. There are also a couple of regularization methods that may help you in overcoming the overfitting issues, especially like dropout, data augmentation, which we discussed yesterday and all, but it doesn't make the model faster. Doesn't make it. I mean, the training process is still not faster, although it may help in addressing the overfitting issue, but still the question lies here is that how to design a model or how to train the model faster, right? So before I again discuss the transfer learning concept under different scenarios, how to choose or how many layers you should or train, I mean how many layers you should fine tune and all. So let us also discuss the same concept whatever has been discussed yesterday, right? The explainability of CNN, right? So what CNN learns at the initial layers and at the final layers, especially, right, or in the later layers. So what you have also seen yesterday that CNNs initially learn, especially it learns generic features. You can see the edge-based features, the orientations, colors, blobs, different types of blobs, right? So these are all called as generic features. So CNNs learn generic features or simple features like edges, color, and blobs, right, at the initial layers. And if you go to the final layers or the later layers, it tries to learn abstract or very specific features, right, which are data specific, or you can say dependent on the data. So this idea is very, very important to understand the concept of the transfer learning, right? So CNN learns generic features at the initial layers, and it learns specific features, or you can say specialized or abstract level of the features at the final layers or at the later layers. This is very, very important to learn. So now I'll jump to the the concept of the transfer learning. So in case of machine learning, if you'll be given 3 different tasks like task 1, task 2, and task 3, so what you know that you can design 3 different learning systems or 3 different model to solve this problem. Now we'll see what do you mean by transfer learning. So transfer learning says transforming the knowledge from a particular model which is learned from different source tasks to the model, right, on which or through which you are trying to solve the target task. That means you are simply trying to use the knowledge that has been learned over several source tasks, right, to help the training process of the new model, right, on which you want to, we can say, train the model, especially on the target task. We'll see that what are the different, we can say, factors that influences this, right? So we have several pre-trained models, we know, right? Like AlexNet, we have AlexNet. These are all pre-trained, right? We have ResNet, we have HGGNet, we have DenseNet. We have all these networks, pre-trained models, right? That has already been trained on a large-scale data set known as ImageNet. So ImageNet is a large-scale data set on which these models have already been trained. So what is our goal? We want to use these networks, right, which has already been trained on large data set to solve our problem, right? So, but this ImageNet only contains natural images, right? It doesn't contain, let's say, medical images or other types of images. It contains only natural images, right, on which it has been trained. And ImageNet contains 1,000 number of classes. Right? That means these models have been trained on such a data set which contains 2 million images and 1,000 classes. So our goal is to just use that network through the transfer learning concept or by transforming the knowledge to solve a similar type of task. We'll see. Goal is just to reduce the training time, the hyperparameter tuning we require, and obviously the goal is also to reduce, or the goal is to also remove the need for the high-end computing hardwares which are required if you want to train the model from the scratch, right? So we don't want to design our own model like ResNet and train it from the scratch, right? So we know that the model has already been trained. It is readily available with us. What we can do is we want to just use those models to solve our problems. So how to use those? How to use these models? So there are various ways to use this, right? One way is only parameters of the classification layers can be trained. We'll see, and the rest of the network is frozen. Under what conditions you should choose this one? you will only train, or you can say fine tune the classification layer, and rest others layers will be frozen. Another case could be you can use this pre-trained weights, right, as the initialization one, and the entire network, right, is then further fine-tuned for better modeling the target task. We'll see. But all these things actually depend on variables such as data set size and the similarity between the target and the source data set. Whether the target and the source data set on which AlexNet and ResNet has been trained are same or not. And what is the size of the data set which you are dealing with? Right? What is the size of the data set which you are dealing with? Fine. Just a second. Yes. So we'll see three different scenario where the data set is small and the target and source data sets are similar. That is one scenario. One scenario could be when the data set is small and the target and source data sets are dissimilar. And there can be another scenario where the data set is large, right? We'll first discuss data set is small. That means the kind of data set which you are dealing with is very small, right? That means that is your target data set. If the target data set is small and the target and the source data sets are similar. In that case, what you can do is you can only think about, right, fine tuning, or you can randomly initialize the classification layer, and rest others will remain same. But we know that yes, CNN at the initial layers used to learn generic features, and at the final layer it used to learn the specialized features. Since the target and the source data sets are similar, that means the generic features as well as the specific features is going to be same. So you should not change these features because these features may work well on your data set, and you do not have also much data here to fine tune the other layers. So what you can ultimately do in this case, so you can only fine tune, or you can only randomly initialize the classification layer. That means what you have to do, you know that yes, the AlexNet was trained for 1,000 number of classes, and if your problem statement, or if your data set is only containing 10 classes, so you can just remove the last or the final classification layer of the AlexNet, replace it with a new layer here, right, having 10 nodes, right, having 10 nodes. And then, right, you can, that means you are now randomly initializing the weights, right, associated with this layer, and what is your job is to just train this layer, right, and rest others are going to be frozen. This is one scenario. Another scenario could be here. If the data set is small and the target and source data sets are not same, data set is still small, right? And the target and source data sets are not same. They are completely different. In this case, what we usually do, because the data set is different, right? It is different because the source data set and the target data set is different. So we cannot consider, right, the specialized features for further processing, because this was specific to a source data set, which is now different to the target data set. But what is common, we know that those are generic features. So what we usually do in this scenario, we usually take the generic features from the general, basically the initial layers, and then we pass those features to some of the machine learning classifier to solve this problem. Because the data set is small, and this specifically the features, like the specific features we cannot consider here. We need to only consider generic features, right? So that means what we are trying to do here is we are simply passing input image to the pre-trained model like AlexNet, and we are trying to extract features from the generic layers, right? That means from the initial layers, right? From where we are getting the generic features. And then you can use any classifiers to solve the problem. The last scenario could be when the data set is large. Now you are having more data with you. So what you can do, if you are having more amount of data, you can think of fine tuning more number of layers, right? Sometimes you can fine tune few layers. You can also fine tune all the layers if the data is different. I hope it is clear, right? If you need to first check that whether the data set is small or large. Here the data set is large, right? So that means you can fine tune either few layers here, or you can also fine tune the whole model. So whenever you are thinking about fine tuning the whole model, what does it mean? That means you are simply using the pre-trained network in that case as a good initialization point, right? So that means you are not taking the random values with respect to each of the filter coefficients. You are taking the pre-trained weights as the initialization point, and then you are fine-tuning all the values according to the data set, whatever is given to us, right? So but while fine tuning, you need to keep in your mind several things. That is, the learning rate should be kept low. It should not be very fast, so that the pre-trained parameters will change rapidly, right? So the learning rate should be kept very low, right, in this case, while fine tuning the layers, right? So it's up to you that how many layers you want to fine tune, as I mentioned, right? So, but it again, if the data set is really large, so then you can also fine tune all the layers, right? But fine tuning all the layers may take more amount of time, but less than the compared to the model which you are training from the scratch, right? So we'll discuss more about it again in the hands-on session. Now let us discuss, right, the most important concept of this, that is what is known as attention mechanisms, right? Yes. So humans naturally and effectively find salient regions, right? So it is natural to us. If I show you some picture and ask you, right, something, let me show you one picture here, and if I ask you what is the boy doing, automatically, right, your focus will only go to this particular region. Because my question here is, what is the boy doing? You will definitely pay attention to the this important regions, right? According to the questions which I'm asking to you, right? So this is natural to human being. So what we want, so we got inspirations from this, whether the model is also focusing on this part while taking the decision or not, because we don't need other parts right now, right? So model should also focus on this part while suppress, right, the informations that are available on the other parts. So is my model, taking decisions, right, based on this. So why actually we want this? Just want to enhance the trust factor of the model, right? So that anyone can believe our model, that the way we are solving the problem, our model is also solving the problem in the similar manner. And that is why attention mechanisms are very important. So the kind of, right, convolutional neural network which you have seen, sometimes it may fail to focus on all relevant artifacts, right, and suppress the other things or the unimportant informations in the image, right? So what is our goal here? So goal is to just improve the representation of interest. That means we want to focus on the essential features while suppressing the unnecessary ones. Mathematically, we can call this attention mechanism is nothing but a dynamic selection process. I will explain why it is known as a dynamic selection process and what do we want to select here, right? Which can be realized by adaptively weighting the features according to the importance of the input. And what has been seen in the literature, that by introducing the attention mechanisms into the convolutional blocks or into the convolutional neural network, right, the convolutional neural network is giving significantly improved performance. And the focus of the model is really better. I'll show you with a couple of examples that how attention is helping to focus, right, only on the important regions compared to the others. Fine. So attention, yeah, this is what I was discussing, that you will pay attention to the relevant artifacts only. I'll show you one demonstration over here, especially one example, especially, right? So you can see here, this is one example which I've taken from this paper, and the task of this of this particular paper is nothing but image captioning, right? So what we want to see here is, while the model is generating a caption, whether it is focusing on the right part of the image or not. You can see here, so there's a woman and there's a child here, and the woman is throwing a frisbee. So when the model is trying to generate the word woman, it is now focusing on the woman. Now you can see over here. Right? And when the model is trying to predict or trying to generate a word known as frisbee, it is now focusing on the frisbee. And when the model is trying to generate the word park, right, apart from this, right, women and the children, so it is focusing on all other parts here. So that means this will enable us, right, to increase the thrust factor of the model, right? So that is why it is very, very important, right, whether my model is really focusing on the right part or not, like the human being. So in general, attention models are of two types, that is hard and soft attention. I'll also talk about another categorization of the attention mechanisms, right, in a while. But this is what about this hard and soft attention? You can see over here in hard attention, you need to only choose one particular region in the image, and then you need to focus on that particular input to solve the problem. But soft attention says no, you can focus on any part and you can assign weights to the different parts of the image, which is really important for us. So attention mechanisms, if you go through the literature, you will find this is a very interesting paper, right, by Gu et al. In 2022, you will find. So this is a survey paper in attention mechanism in computer vision, right? So because you will also find the concept of attention mechanisms in natural language processing, you will also find, some of the attention mechanism that is initially been applied to natural language processing and later been adapted to computer vision domain, right? So what are the two important types of attention mechanisms we have? So one is channel attention and one is spatial attention, right? And you can also find in the literature that people have combined both channel attention and spatial attention together. So there are a couple of examples, or there are a couple of techniques, right? You will find starting from 2018, 19, that you will find different types of attention mechanisms people have developed. And over the years, people have also proposed a variant of the channel attention mechanisms, spatial attention mechanisms, and most popularly known as the self-attention mechanism, which is currently being used in Bayesian transformer architectures. Right? I'll show you one type of channel attention and one type of spatial attention today, including the self-attention, right, which also comes under this spatial attention category. But yes, people have also developed self-attention mechanism, which comes under this channel attention category. Right? Okay, we'll see one by one. Channel attention. I'll start with channel attention. But before I discuss, channel attention, let us try to understand the mathematical, concept behind this attention mechanism. As I mentioned earlier, that it is nothing but a dynamic selection process. And how can we represent any attention mechanisms with the help of these expressions? We can analyze or you can express any attention mechanism, right, with this expression. What is this? That is f of g of x, x. So this g of x is nothing but the attention score. And it will vary from definitely attention mechanism to attention mechanism. This x is nothing but the input on which you want to apply the attention, right? This is how we can represent, right, any attention in the form of a mathematical expression. We'll see how to define this g of x in case of a channel attention, and what is this g of x in case of spatial attention, right? And the whole function is nothing but an attention function over here. Fine. So that means what you are trying to do here is you are processing an input based on an attention score, which is nothing but g of x, right? And the whole expression is nothing but tells us the functionality of the attention mechanism. I'll come back to these two equations later on. Let me first discuss what do you mean by squeeze and excitation, which is nothing but a kind of channel attention which we have. So what do you mean by channel attention, first of all? And in this case, what we want to select? because what we have seen that it is nothing but a dynamic selection process. So what we know that we have seen, right, the output of or the output after the convolution operations. The output after each convolution operation is nothing but a set of feature maps which are stuck together, and we sometimes call it as a feature map or feature volume. And if you look at this particular feature map is having size H cross W cross C. What does it mean? There are C number of channels. Obviously, you might have used C number of filters in the previous layer. That's why you are getting C number of channels over here. And this is the spatial resolution. H is the height, it represents height, and W represents here width. This H and W is nothing but the spatial resolution, and C is nothing but the number of times you have applied the filters, and now it is called the depth of the feature map, or you can call it as the number of channels that are present in this feature map. So different channel, we are having C number of channels. Not all the channel contains input and informations, and different channel contains different types of informations of the objects which we are looking at. So how to highlight, right? Only the important channels and suppress the other channels. We are not removing any channel over here. We want to highlight only the important channels out of the C channels. That is what is our goal here. So what we ultimately want to do here is we want to find out the C number of weights. We want to find out C number of weights, and then we want to multiply that weights, right, over each of the C number of channels, or over each of the C number of feature map we have. And then what we will get is nothing but a weighted feature map, and we are calling it as a refined feature map or attention feature map. And based on these weights, you know that you can highlight the importance of the channel. But from where we'll get these weights? It is nothing but a just weighted multiplication. From where we'll get these weights? We don't want to provide a fixed weight to C number of channels, right? Because this may vary from input to input. That's what we know. So we cannot fix a single value over here. We want these weights to be learnable, right? We want to adaptively change this, or we want to make these weights learnable. So then what are the steps that has been followed in squeeze and excitation, which is nothing but a channel attention? I'll show you. First, this is the size of the feature map. I hope it is clear. What is H cross W cross C? That is the input size, right? And first, what we will do is we will apply a global average pooling over here. So if you apply a global average pooling operation over this feature map, that means you are applying global average pooling over each of the feature map. So what you will ultimately get is 1 cross C. Corresponding to every channel, you will get a single value. So we are having C number of channels, and you are trying to find out the global average of each feature map, right? So ultimately you will get C number of values, but these values cannot be directly considered as the weights because we want to make it learnable. Either you can use a fully connected layer over here, or you can use a 1 cross 1 convolution to make it learnable. You can apply 1 cross 1 convolution over here. So in squeeze excitation, why the name is called a squeeze and excitation, they have first applied 1 cross 1 convolution, right? C by, let's say, 2 times or C by 4 times. We can in general write C by R times. And then again, they have used one more time 1 cross 1 convolution C times. And this helps in reducing the number of parameters, right? If you directly use the 2 times convolutions, probably the number of parameters is going to be high. At the end, right, they have used nothing but called as a sigmoid activation function, which will gives us the value from 0 to 1. So that means all the weights, right, all the C number of weights will be nothing but will be nothing but every weight will be having values from 0 to 1. And these weights, right, these weights will be now multiplied element wise with each of the right feature map. I mean, obviously the C number of feature maps we have in this particular volume. And that is the procedure here to obtain the channel attention feature map, right? So we'll be having C number of course, weights. You can see over here, whatever I've discussed, global average pooling. Obviously, the size will be reduced to 1 cross 1 cross C. then FC layer having C by R number of channels, then followed by another FC layer. These FC layers can be easily replaced with 1x1 convolution, so that it will be a fully convolutional network. Right? You can simply replace this FC layer with 1x1 convolution, not a problem. Right? And then finally you have to use a sigmoid activation function over here, which will gives us the value from 0 to 1. And whatever the value you are getting over here, that value will be element wise multiplied across each channels of the input. And what you will ultimately get is nothing but a refined feature, which is in this case x bar or x bar, right? But the input is nothing but x, right? So this is all about actually the channel attention. So where we have got C number of values and provided, or then what we have done is we have made it learnable and then applied a sigmoid activation. What we have got is ultimately known as attention weights, and those weights will be multiplied here to highlight each of the channels, right? So accordingly, let's say the value is more, that means that will be highlighted more. If the value is less, that will be suppressed, right? But that we don't want to decide by ourselves. We want to make it learnable. That is what we have done. And here are some of the results, right, that you can go through the paper, right, which I have mentioned over here. That's the CVPR 2018 paper known as squeeze and excitation networks, right, where the authors have applied the squeeze and excitation attention module, right, into the resonate architecture and other architectures. And here is the result you can see over here on the very popular ImageNet data set. The error rate you can see over here. The error rate is really less compared to the other architectures using this squeeze and excitation attention. Fine. So the next is another very popular attention mechanism known as CBOM, convolutional bottleneck attention module. Yeah. So what we have seen is that how to select how to highlight the important channels, right? So what we should also look at that which of the positions are important for us, right? Out of the all spatial positions we have. So you could see, I think there are some doubts in the chat box probably. Let me read it out. Channel here, sir, RGB. No. It is feature map. We are not talking about the channels RGB. There are only 3 channels. No. Whatever the features, right, the CNN has learned, it contains multiple number of channels, right? Whether all channels are carrying important information or not. You also know that yes, not all the channels carry important informations. So we only want to highlight that channel which carries important information and suppress the other channels, right? That is what is channel attention is all about. And we have discussed about one of the approach, right, which is very popular, known as squeeze and excitation. You will also find several other approaches, right, on this channel attention, where they have included even frequency based attention also you will find. So multiple types of channel attention you will find in the literature, but the concept is very same, that for every channel you need to identify or you need to learn a weight and then multiply that weight with respect to all the channels you are having in the feature map, or you can say the feature volume. Fine. So we have just now identified that which of the or selected which of the channels which are important for us. So similarly, we can also identify which of the positions are important for us out of all the positions we have. Not all the positions carry important informations, or not all the positions are important for taking the decisions, right? So we can only highlight those positions which are important for us. So how to do this, right? How to do this? So in CBOM, especially when it was published again at the same time in 2018 in again a STAR conference, ECCV, right? Convolutional bottleneck attention module. So the name is so-called CBOM, right? So basically it tells us that where to pay attention, right? This is the message here. Where to pay attention. In case of channel attention, it is what to pay attention, right? So if you look at this particular attention module, what it does, it sequentially applies channel attention followed by spatial attention. So what we have discussed right now is only channel attention, right? So what do you mean by spatial attention and how to perform spatial attention over here? So what we are having is only right a feature map having size, let's say H cross W cross C. That means again we are having a feature map, right? I'm considering feature map at any layer where the spatial resolution is nothing but H cross W and C is nothing but the number of channels we are having. Now we are interested in identifying the important positions out of all the spatial positions we have. So that means the weight matrix, in this case, the weight should be a matrix, right? Previously it was just a single vector because there are only C number of channels. But we have H into W number of positions we have. So what do we want? We want to also build a attention weight matrix, and this is going to be a two-dimensional matrix over here. So we want to find out weights, right? We want to learn weights with respect to each of the weight, and based on these weights, right, it should highlight which of the positions are important for us. How to get this two-dimensional attention weights. So previously we have applied actually global average pooling over each of the feature map, and for every feature map we have got a single value, and that's why we got C number of values. So now it is different. You'll get an attention, right, weights in the form of a two-dimensional matrix because we have input in the form of a two-dimensional matrix, right? So then how to do this? You have to apply, right, the operations across the channels. So what you can do is you can apply a max pooling, or you can say global average pooling or a global max pooling operation over each of the pixels, right? That means every pixels in this feature volume contains C number of values. So you have to take the global average pooling across the channels. If you take or if you can apply the global average pooling or global max pooling across the channel, so what you will get is ultimately nothing but a single, right, two-dimensional matrix where every point or every point or pixel in this particular feature map is nothing but the global averaging of all the pixels across the channel, right? And then what you can do is you can simply apply, right, convolution operations over here and followed by a sigmoid operation, right, to make it learnable and to normalize the value from 0 to 1. And finally, you will get a two-dimensional matrix having size H cross W and all our weights, values, right, lying from 0 to 1. So this will be again multiplied with these weights, right, which is 2D in nature right now, can be directly multiplied with each of the feature map element-wise, and then what you will get is nothing but, again, a refined version of the input, which is H cross W cross C. The input to the attention model and the output to the output of the attention model both are same. So what we are only getting is nothing but a refined version of the attention. That means you have in this particular spatial attention, what you have done, you have just multiply, right, with the weights whatever you have learned, right, here with each of the positions to highlight the important positions from the image. What we have discussed is one type of spatial attention and one type of channel attention. Right? In CBAM, what they did is they have combined, or you can say they've combined the channel attention and spatial attention together, right? And which are connected in sequence. If you want, if you go through the literature, you will also find that people have taken or people have applied this channel attention and spatial attention parallelly. Over the same input, they applied channel attention. Over the same input, they applied spatial attention. And finally, they combined the output either by taking the average, either by taking by performing addition or by considering concatenation operation, whatever, right? So they have fused the output, and then that output is nothing but the refined output, or you can say the final attention-based output, right? So multiple things have been done in the literature, but these are two basic, you can say, right, attention mechanisms which are very, very popular and even currently being used by many of the researchers across the globe. I can show you some results, right? Whatever is reported in the CBAM paper, you can see over here, right? And these things, right? These are nothing but the GradCam maps, which we have seen in the yesterday, right? So these are some of the input images we have, right? You can see over here. So there are 8 input images, and here is the GradCam visualization results, or you can see the heat map visualization results, right? Over each of the image, you can see over here that ResNet only is because it is the class level, or you can say the class level particularly for this image is nothing but a croquet ball. So it is not only focusing on this ball but also focusing on this particular person, right? So which is not correct, right? It should only focus on, because the class level is only croquet ball, it should not focus on other parts. It should only focus on this part, and it is still, the ball is here only, but it is still focusing on the other parts. So the ResNet, when the squeeze and excitation is applied over the ResNet, so it is now, it is now not focusing on the person, it is only focusing on this part. But if you see the output, right, with the CBAM, right, it is more, you can say, focused towards the particular region of our interest, right? So similarly, you can find the same thing for other examples, right? How the CBAM is helping, right, the model to accurately focus on the relevant regions. You can see over here for the snow leopard, it is fully focusing on the overall part. But in case of squeeze and excitation, because it only contains general attention, not the spatial attention, it is not focusing properly on the other parts, right? So these are the parts which is not focusing. Even you can see, only ResNet. I mean, the model that's the CNN model without any attention. It is not able to focus on the, on the perfect part, or you can say the correct part. Similarly, you can also see some other examples over here, right? How the CBAM is helping the model to accurately focus on the relevant regions. One more attention, right, which is very, very important nowadays, is nothing but called as self-attention. So you'll also find the different variants of self-attention available in the literature. So this is, right, the self-attention mechanism which can be applied directly over the image matrix, or you can say the feature map. If the feature map is having size H cross W cross C, so how to apply the self-attention mechanisms, right? So in self-attention, you might have, I think Professor C. Chandrasekhar already discussed about self-attention. We have also a separate, session on transformer, where again this part will be discussed. I'll just briefly touch upon how the self-attention is different from the kind of, right, attention which we discussed, which is known as channel attention, spatial attention, which are local in nature, but we call the self-attention is global in nature. It is a global attention technique, because it tries to find out the relationship or pairwise relationship among each of the pixels that is present in the feature map. Right? We'll see how the attention, or what is the size of the attention weights here, or attention score. We've seen the size is nothing but here 1 cross 1 cross C in case of channel attention. In case of spatial attention, it is H cross W. These are the weights. But in case of self attention, it is something very different. It is HW cross HW. We'll talk about it, how to get this, how it projects the input image into 3 different projections. We call it as key, query, and value, right? Query projection, K projection, and value projection. So how to get this? So you have to apply 1 cross 1 convolution over here, over the input, right, to get these 3 projections. After projections, what you will get is H cross W cross C, and H cross W cross C here. You can just resize it to HW C, or sometimes if you want, you can also reduce the number of channels over here. If you want, you can reduce the number of channels. If the number of channels are right now C days, you can just make it C days. You can also you can resize it to HW cross C days, and here you can again resize. It will be HW cross C days. You can also take a transpose over heat. You can get C days cross SW. Then you can multiply, right, Q into K transpose, right? So you can just multiply these 2 matrices. It is a traditional matrix multiplication, right? It's a simple matrix multiplication. If you multiply HW into C dash cross SW, what you will get is SW cross SW. And here the kind of activation function which is used to get the attention score is something called as softmax. So what it basically tells over here, what is SW cross SW? It is trying to find out the relationship, you can say the dependencies of each particular pixel with respect to every other pixels in the image. That's why it is known as, it tries to capture the pairwise interactions among the features in the feature map available with us. So let's say, for example, if the image is having size, let's say 7 cross 7 cross 64, the feature map is having size. So that means how many pixels we are having? We are having 49 pixels and we are having 64 channels. And what this attention score tells us, that the size of the attention score matrix is going to be 49 cross 49. We are having in total 49 number of pixels, right? So that means what it tells is that how the first pixel is related to all the pixels, right? So we're trying to find out the dependency of the first pixel with respect to all the pixels, right? And the dependency has to be, and that is why actually they have applied over here softmax activation function, right? So that the total value if you add across the row is going to be 1, right? And then in the next for the next pixel, how the second pixel is related to all other pixels that is present in the image. So that means you are trying to find out a global relationship over here, which is very, very important. This is why actually, it is very, very, popular nowadays to find out, or you can say to extract global information from the image, where you want to find out the relationship between each and every pixel that are present in the image. So what is the next step here? The next step, after getting this particular attention score, you can just multiply it with the value, right? The value projection over here, you can see the value matrix, which is having again size HW cross C. And I mean, after resizing, you can get the value as HW cross C, and then you can just multiply SW into SW into SW cross C, and ultimately what you will get is HW cross C, and then you can just resize it and get back to the original size S cross W cross C, right? So this is how actually we apply, right? The self attention mechanism, and the size is here only as W cross SW, right? So that means we are only trying to find out the global relationship across this spatial dimension, not in the channel dimension, right? So that means we have just found out the pairwise relationship among each of the pixels, not among each of the channels, right? So this is actually by default that the self attention, right, the self attention actually comes under the spatial attention category. But if you want, you can also design a self attention, right, which will compute the relationships channel wise. In that case, the attention score matrix is going to be C cross C, where you can compute the relationship of one particular channel with all the possible channels we have, right? So also, I mean, we have also worked on it, right? How to design a channel wise self attention module and a spatial wise channel attention module, and then how to combine them, right, either sequentially or parallelly, right? So this particular self attention mechanism is very, very important, right, over the images. How to apply, but there are traditional self attention mechanisms, if you find, where you need to first convert this particular feature map into a one-dimensional vector, and then only you can apply self attention, right? You can also, if you want, you can directly also apply the self attention mechanism in this manner, right? So the spatial relationship is not going to be lost. And this is the traditional VIT architecture will be discussed later, right? And how I mean, where actually we are using this particular self attention, we are applying the self attention multiple times, and we are calling it as a multi-head attention. Basically, we are applying this attention in the transformer endpoints, right? So you can apply, if you want multiple times, you can apply the attention, right? And then you can just concatenate the output, right? And that will become nothing but called as multi-head attention. Right? So there are a few case studies I'd like to show you, right, which we have been working on. I mean, 2 problem statements, right? So there is one problem statement is like brain tumor classification. Our goal is to classify the brain MRI image into 3 different types: glioma, meningioma, and pituitary. These are all 3 tumor types, right? And this is one of the attention mechanisms which we have proposed in 2021. The paper was published in ICIP, 29th International Conference on Image Processing, one of the very popular and oldest conference in the field of image processing, right? So where we have just developed something called as something called as a channel split dual attention block. You can see over here. So first we have actually splitted the whole picture map into two different parts, and then we have applied a positional attention block and a channel attention block together to design the whole attention mechanism over here, right? So the details will be found in this particular paper. Fine. Here is the results, whatever we have obtained. So these are original images. So these are, the GradCam visualizations without attention, right? Using only the dense net pre-trained architecture, right? Again, we have used a transfer learning concept over here, but we have inserted the proposed attention, whatever we have developed, right, into the dense net architecture, right? Now you can see how the model is focusing only on the relevant part. So these are the relevant part, but here the model is focusing on other parts as well, right? You can see over here other two samples, right? Other two examples where our model is trying to focus better, right? Only on this particular part, right? But here in this case, the model is focusing on also some other relevant parts. You can see over here. Here is just a comparison between the kind of attention mechanisms which we discussed, CBAM and squeeze and excitation. You can see over here, along with all possible types of backbone which we have considered. So in all the cases, this is particular attention which we have developed is performing better compared to the CBAM and squeeze and excitation which we discussed. Here's just an example, right, which I have taken from one paper from IEEE transaction on instrumentation measurement, a cross-lesion attention network for accurate diabetic retinopathy. So these are all actually fundus images, retinal fundus images used for diagnosing several ophthalmic diseases or eye diseases. And this particular paper is only focusing on diabetic retinopathy disease, right, which is caused due to diabetes and a kind of eye disease. And these are actually some of the regions which we should focus on. Some of the regions. Fine. You can see over here how the model is correctly focusing only on the important regions and suppressing the other regions, right? So this is how we can increase the trust factor of the model, right? Or you can say this is what is actually we call it as interpretability or the explainability of the model. Why the model is performing well. Another example on breast cancer classification through histopathological imaging, you can see over here. So it's very, very difficult to identify, right? And basically classify actually these type of samples because all are looking very similar over here. Will not, I'll not get into the details of this histopathological imaging and all. I'll only try to show you that the kind of performance which we have got, right, by using some of the attention mechanisms which we developed. So recently we have developed an attention mechanism. It's just a variant of self-attention mechanism. You can see over here, which is known as deformable self-attention mechanism. So deformable, there are different types of actually convolution operations that have been proposed over the years. So deformable convolution is one among them, which is very, very important to adapt to objects of different shapes and different size. Right? If the object varies sharply in terms of size and shape, so this kind of convolution operations, right, is going to be very, very important, right? Because the normal or the traditional convolution only focuses on the either the square region or the triangular region of 3 cross 3. But if you want to actually arbitrarily capture informations from different regions, right? So this kind of convolution is going to help us. That is deformable convolution. We have introduced this deformable convolution into this self-attention mechanism. You can see over here, right? So this is a kind of self-attention mechanism which we have just now discussed. You can see SW cross SW is nothing but the size of the attention score matrix, which is again multiplied with the value over here. We have introduced some deformable convolution over here. And this is what is the layer which we have introduced, called as a residual deformable transformer layer. So what we have done here is specifically we have first taken a CNN based network, you can say backbone network, which is nothing but a pre-trained image network. It can be anything. It can be DenseNet, it can be ResNet and all. And then the kind of feature which you have extracted from the CNN has been now passed to a transformer layer. So that means what we have done, we have combined the benefits of both CNN and VIT together. Because we know that CNNs are good at extraction of the local features, but CNN cannot extract, or CNNs are not good at extraction of the global features. But global features can be extracted easily with the help of transformer concept, right? Especially with the help of the self-attention mechanism. So what we have done here is we have just tried to capture both local as well as global features, and what we have obtained is a very you can say improved results, right? While only considering local, while only considering global, if you compare. So then what you will see that yes, our particular attention is giving or helping the model, right, to capture the global information along with the local information, and ultimately helping us in improving the performance. This is one of the varieties, and if you go through our recent papers, you will find we have also introduced frequency-based concepts into the attention mechanisms. We have also used several different types of things we have developed. We have also introduced Hoji concept into the attention mechanisms, how to deal with the uncertainty, right? So there's also one work which we have done on attention-based mechanisms. And let me show you the visualization results. So you can see over here. So these are all histopathological images from different categories, and especially from the benign categories, which is mentioned over here, at different magnifications. So this is one image at 40x magnification, at 100x magnification, 200x and 400x magnification. You can see over here. So these are actually the lesion, or you can say the lesion areas or lesion regions in the image that is present over here, right? So if you are only using a baseline model, either convolutional neural network or vision transformer model, it is only focusing on only one particular region here, but these other regions, especially this region and these regions, are not focused properly, right? So but with the help of the kind of attention mechanism which you developed, now you can see this one, all these important regions are correctly identified and correctly focused. Similarly, you can see other examples over here. Fine. Yeah. So yeah, that's all actually about these attention mechanisms and all. If you want, you can explore much. I've also shown you one article, right? One survey article from where you will get to know about the different types of attention mechanisms that have been proposed over the years. So what we've seen, only channel attention, spatial attention, there is something called self attention. I've also given some idea that how to introduce, let's say, channel wise self attention, and how to just combine them together. People have also worked on it. People have also worked on how to reduce the number of parameters, right? So one thing that comes to your mind, that yes, we have introduced some convolutional layers into the attention mechanisms. So that means we are increasing the number of parameters by introducing the attention mechanism, right? Although our goal is to focus on the important regions to mimic the human vision system, but still, right, there's a possibility that the number of parameters are going to be very high if you are introducing more number of attention layers. So people have also worked on designing lightweight attention models, right? You can also think of designing lightweight attention models which doesn't take a much number of parameters and flops, which are very important. So people have also done some work on it. Still people are working towards designing lightweight attention based mechanisms, right? So if you're having any queries, you can write in the chat box, right? I'll be happy to answer your questions. Can we combine? I can see some questions. Yeah, from Sweta, can we brief temporal attention? Okay, if you're dealing with videos, then we need temporal attention. Can be done. Temporal attention in the similar manner, right? You'll be having another one that there is something called as temporal dimension in videos, right? You can think of designing temporal attention in the similar manner, the way we have designed for channel attention and spatial attention. That is possible. Or can you refer? Yes, I will definitely refer you I will share the link of the paper, right, from which you can get the information about this temporal attention. Very similar to the concept which we discussed today, right? So can we combine these attentions like C-bomb with transformer? Yes, yes, why not? You can combine if you want. So see, this is the current trend. Nowadays, people are combining convolutional neural network and vision transformer together. Called it as and they are calling it as convolutional transformer, or they're calling it as conv-VIT. This is the current trend, right? So, you can combine. If you want, you can just combine convolution with VIT, right? If you want, you can also combine the attentions like self-attention, C-bomb together, right? It is possible. Whether this attention should be applied, yes, yes, that is the question, right? Whether the attention should be applied to the layers, or can we apply it a particular layer? So the literature, what you will find that most of the, most of the researchers, right, introduced the attention mechanism at the end of, basically at the later layers, right? As I mentioned that, yes, because these layers, these attention layers introduces some sort of parameters, so it is not easy to introduce after each layer, right? And some of them also mentioned that, yes, we will only apply the attention to the specific, or you can say the abstract level of the features. So we know that the later layers in the CNN always gives us information about the you can say the specific object, whatever that is present in the image. So we will only apply to that layer and we'll get the results. So also people have got success. But if you are having, such a attention mechanism which is lightweight nature and which can be combined with every layer, so that also you can explore, right? So there are also papers where you will find people have designed attention mechanisms that they have introduced after each of the convolutional layer, which of whatever they have designed. That is also possible, but you need to only take care that that whether it is trying to introduce more number of parameters or not. So if it is in by introducing more number of parameters and you are dealing with a very small data set, again you may suffer from some overfitting issues and all. So for that, all right, the performance may degrade. So that also you need to check. How to reduce the number of parameters and G-flops in such CNN plus attention mechanism based model. Okay, see. So that's what I mentioned, right? So I mean, one example I've given to you, that instead of like in let's just let us consider squeeze and excitation, right? In squeeze and excitation, whatever we have discussed, right? In case of squeeze and excitation, that they are using two convolutional layers, right? Two convolutional layers. So you can just reduce one convolutional layer and check the performance, if whether it is performing well or not. That may also reduce the number of parameters, right? So there are various ways to actually reduce the number of parameters. People have even not used the convolutional layers here, right? People have only used one convolutional layer instead of the two. So they have suggested to use two convolutional layers, and that they have also suggested to take filters. For the first time, whenever you are using a convolutional layer, then you take C by R number of filters, and next time you take C number of filters, right? So that is how actually they try to reduce the parameter, but still you are using two number of filters over here. So for which, especially two number of convolutional layer, so for which you may get, right, even many number of parameters, right? So that is, there are various ways you can explore that, how to reduce the number of parameters. Then attention mechanism, because using both together it will be high, of course, of course. GradCam is explainability technique, explainability or attention. No, GradCam is explainability technique. Through attention, we are just trying to look at whether the model is focusing on the important part or not, but because that is what is the goal of the attention mechanism, right? Whether it is focusing on the accurate region in the image or not, right? So that is what is. So how did we get this? So we get this with the help of the GradCam visualizations, which is basically used to, you can say, prove the interpretability or the explainability of the model, right? And attention helps in focusing to the accurate regions of the model. I'll share you few, papers. I mean, basically where you will find that people have also developed few attention mechanisms with a very less number of parameters. Dr. Aditi, I'll share with you, right, some papers, right? Even you can also search parameter-free attention mechanisms. There is also a paper known as parameter-free attention mechanism, where you will find there are no parameters, but still it is giving good results. Yes. Any other queries? So any other queries you are having? I think there are no other queries. So I can stop here because we'll start on next session at after 5 minutes. So if you're having any doubt, please drop an email to me. I'll get back to you, right?